Pluto is a far-off and perplexing smaller planet that was once a member of our planetary systems family. However, recent astounding statements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They suggested that this cold world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a major event? Are we witnessing an unexpected cosmic anomaly, or is there more to this looming celestial collision? Join us as we explore the potential outcomes of a Pluto-Neptune impact. Pluto, a former planet that was downgraded to a dwarf planet, remains a subject of fascination and study in the cosmic community. According to recent figures by leading scientists, Pluto's orbit comes dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially catastrophic collision between these two planets, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution yet. The intrigue doesn't stop there. Pluto's orbit is characterized by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more curious is its inclination of 17 degrees to the ecliptic plane. The path Pluto follows is significantly more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital dynamics. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect based on their positions in the planetary system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational interactions of other planets. The analysis of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to understand its unusual path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit projects at a steep inclination with an elongated shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricate mechanics of space. The three-body problem in space involves determining how three objects, like Pluto, Neptune, and the Sun, move and interact with each other due to their gravity. It's like trying to predict their movements based on where they start and how they pull on each other. In Pluto's case, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex way. Key terms like mean motion resonance and orbital inclination are crucial to solving this puzzle. Mean motion resonance refers to the gravitational relationship between two orbiting bodies. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is always at least 90 degrees away from Neptune. This spatial separation is critical in preventing their orbits from crossing. Inclination libration, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned entirely above or below their orbital plane, providing an additional layer of protection from potential impacts. Another important factor in this situation is the VSK oscillation, named after three scientists, von Zeipel, Kozai, and Litov, who studied how objects move in space. This oscillation explains why Pluto's orbit around the Sun is so unusual. Despite its seemingly chaotic path, this oscillation helps keep Pluto moving smoothly for billions of years. The VSK oscillation shows that even though things in space may seem wild and random, certain patterns and forces keep everything in balance. These factors help maintain Pluto's orbit, ensuring it doesn't collide with Neptune or drift away. The three-body problem is essential for understanding how orbits change due to gravitational interactions. Studying this helps us learn more about Pluto, our solar system, and distant stars and galaxies. Numerical simulations in the late 1980s revealed that despite these stabilizing properties, Pluto's orbit is actually chaotic, with slight changes in initial conditions leading to massive variations over time. However, these unique properties of Pluto's orbit have been found to maintain stability over extremely long timescales, effectively keeping the chaos in check. Recent computer models have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a special resonance relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps stabilize Pluto's orbit. But Neptune isn't the only factor. Jupiter's gravity also plays a significant role in safeguarding Pluto's orbit, and Saturn contributes as well. These studies show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for a long time, possibly even billions of years. It's like Neptune, Jupiter, and Saturn are working together to keep Pluto moving safely in space without causing trouble. These dynamics are crucial in the broader context of the universe, maintaining order and stability in the motion of celestial bodies. Without these mechanisms, the solar system as we know would be a much more chaotic place, with bodies like Pluto potentially colliding with others or being ejected from their stable orbits, leading to a ripple effect on other celestial objects. For Pluto, especially in discussions about its potential collision with Neptune in the future, understanding its orbit is essential. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto shows how even the most seemingly unstable orbits can achieve a state of harmony through the intricate interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the enigmatic nature of celestial bodies, and Pluto's orbit is a perfect example of this phenomenon. The concept of orbital chaos, which refers to the sensitive dependence of a body's path on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight changes in its starting conditions could lead to significant variations in its orbit over time. Despite this inherent instability, Pluto's orbit remains remarkably consistent, thanks to the delicate balance of gravitational forces from other celestial bodies in the solar system. This raises intriguing questions about the long-term dynamics of our solar system. Could any external forces, such as passing stars or interstellar objects, disrupt this equilibrium? Such disruptions, while highly unlikely, could have profound implications for the stability of Pluto's orbit and its interactions with Neptune and other planets. Understanding the mechanics of these orbital relationships is not just an academic exercise. It has practical implications for predicting potential cosmic events and safeguarding our planet. For instance, a collision or significant gravitational interaction between major celestial bodies could send shockwaves throughout the solar system, potentially affecting Earth's orbit or its gravitational stability. Moreover, Pluto's unique orbit and its potential interactions with Neptune provide valuable insights into the history and evolution of the solar system. They help scientists understand how gravitational forces have shaped the paths of planets and other objects over billions of years. These studies also inform our understanding of exoplanetary systems, where similar dynamics may be at play. In conclusion, the story of Pluto and its relationship with Neptune is a testament to the complexity and elegance of the universe. It highlights how even the most chaotic-seeming systems can achieve stability through intricate gravitational interactions. As scientists continue to unravel the mysteries of Pluto's orbit, they not only deepen our understanding of the solar system, but also inspire awe at the intricate dance of celestial mechanics that governs the cosmos. Pluto's situation or speed can altogether modify its long-term trajectory within the vast territory of our solar system. Pluto occupies a unique position that challenges our understanding of planetary formation and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant revelations about its composition and behavior. One of the most fascinating aspects of Pluto is its surface, which is a complex tapestry of ice, rock, and various compounds. The New Horizons mission, which flew by Pluto in July 2015, provided incredible data about this distant world. Pluto's surface is characterized by vast plains, towering mountains, and deep valleys. One of the most striking features is Sputnik Planitia, a massive heart-shaped plain primarily composed of nitrogen ice. This region highlights a diverse array of geological features, including large ice blocks and what appear to be flowing glaciers. The presence of these features suggests that Pluto could still be geologically active, despite its great distance from the Sun and low temperatures. Another fascinating aspect of Pluto is its atmosphere, primarily composed of nitrogen, with traces of methane and carbon monoxide. Pluto's atmosphere is thin, but exhibits intriguing seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior reflects the complex interaction between Pluto and its environment. During Pluto's closest approach to the Sun, some of the atmospheric gases may freeze onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that the two bodies orbit a point in space between them, rather than Pluto simply orbiting Charon. This unique relationship contributes to the gravitational dynamics of the area, influencing the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated by small icy bodies, is home to many other dwarf planets and potential impactors. This belt is a repository of ancient material from the early solar system, offering scientists a glimpse into its formation. Pluto's orbital characteristics may provide insights into the migration patterns of these distant objects, suggesting that interactions with larger planets might have played a crucial role in shaping their current orbits. Understanding Pluto's orbital dynamics could have significant implications for our understanding of the solar system's evolution. The gravitational influences of nearby giant planets, such as Jupiter and Neptune, can alter the trajectories of smaller bodies, including those in the Kuiper Belt. Such interactions can lead to changes in orbits, potentially causing collisions or ejections from the solar system. As scientists continue to study these interactions, they may uncover broader patterns that govern the behavior of celestial bodies across the universe. The exploration of Pluto also raises philosophical questions about classification in astronomy. The decision to reclassify Pluto as a dwarf planet in 2006 sparked debates about what defines a planet. The global astronomical community's definition focused on criteria, such as orbital dominance and size, leaving many to consider the implications of such classifications. This ongoing debate reflects our evolving understanding of the universe and underscores the need for a flexible approach to categorizing celestial bodies. Additionally, the potential for future exploration of Pluto and the Kuiper Belt remains an exciting frontier. With advances in technology and mission planning, scientists are considering sending additional spacecraft to study Pluto and other objects with similar orbital characteristics. Such missions could provide valuable information about the primordial materials that formed our solar system, possibly shedding light on the origins of life on Earth. The role of exoplanets, planets beyond our solar system, is another intriguing area of study that intersects with our understanding of Pluto. As astronomers discover an increasing number of exoplanets, particularly those in the habitable zones of their stars, the lessons learned from studying our own solar system may help shape theories about planetary formation and habitability. Finally, public interest in Pluto has remained strong, fueled by its mysterious status and the stunning images returned by the New Horizons mission. The dwarf planet has captured the imagination of people worldwide, inspiring a renewed appreciation for the vastness of space and our place within it. As we continue to unravel the mysteries of Pluto and the celestial bodies that share its corner of the universe, we are reminded of the remarkable wonders the cosmos has to offer. Pluto's extraordinary nature extends beyond its physical properties and orbit. It also serves as a significant case study for understanding planetary evolution and the dynamics of celestial bodies. Pluto's evolution is believed to have occurred in the early solar system alongside other Kuiper Belt objects. Studying its formation can provide insights into the conditions that prevailed during the nascent stages of the solar system, potentially shedding light on the formation of terrestrial planets. Recent research suggests that Pluto may have a subsurface ocean, a discovery that could transform our understanding of its geology and potential to support life. New Horizons data revealed that some regions of Pluto's surface, such as the icy mountains, may be composed of water ice, which behaves differently from ordinary rock at low temperatures. This discovery invites further investigation into the likelihood of liquid water existing beneath its frozen crust, raising intriguing questions about the potential for life even in such extreme conditions. Moreover, Pluto's interaction with its atmosphere can offer insights into atmospheric science. The seasonal changes in its thin atmosphere provide a natural laboratory for studying atmospheric cycles on a planetary scale. Scientists are particularly interested in how the interaction between solar radiation and the surface can lead to complex weather patterns similar to those observed on larger planets. The importance of continued observation of Pluto and other similar celestial bodies cannot be overstated. Through missions focusing on the outer regions of the Kuiper Belt, we can expect a wealth of new data that challenges existing theories and expands our understanding of planetary science. Pluto's role in advancing planetary science is pivotal not only in understanding its own characteristics, but also in shedding light on the broader dynamics of celestial systems. Its diverse geology, complex atmosphere, and unique orbital relationship with Charon make it a prime subject for future investigations. One key area of interest is Pluto's potential for hosting a subsurface ocean. If confirmed, this could have profound implications for astrobiology, as the presence of liquid water beneath an icy crust is a key factor in assessing the potential for extraterrestrial life. The hypothesized ocean may be kept liquid by heat generated from radioactive decay or tidal forces resulting from its interaction with Charon. In addition to studying Pluto's potential ocean, future missions could explore the intriguing connections between its surface and atmosphere. For instance, scientists are interested in understanding how seasonal variations in sunlight drive changes in Pluto's thin atmosphere and lead to the deposition or sublimation of surface ice. These processes provide a natural laboratory for exploring the interaction between surface and atmospheric chemistry, which may have parallels on other icy bodies in the solar system. Furthermore, the study of Pluto's position within the Kuiper Belt offers insight into the early formation of the solar system. As a representative of the icy bodies that dominate this distant region, Pluto serves as a window into the conditions that existed billions of years ago. By comparing Pluto's composition and orbital characteristics to other Kuiper Belt objects, scientists can piece together a more comprehensive picture of the solar system's early development. This understanding extends to the migration of the gas giants, whose gravitational interactions likely played a major role in shaping the orbits of smaller bodies like Pluto. These migrations may have caused significant reshuffling of material in the outer solar system, influencing the composition and distribution of planets, moons, and smaller objects. The New Horizons mission was a monumental step forward in our understanding of Pluto, but it also raised as many questions as it answered. What lies beneath its icy surface? How does its complex relationship with Charon influence its evolution? Are there other dwarf planets in the Kuiper Belt with similar characteristics waiting to be discovered? To address these questions, scientists are developing new mission concepts that could include orbiters or landers to explore Pluto and its surrounding environment in greater detail. Advanced technologies, such as miniaturized instruments and more efficient propulsion systems, could enable these missions to provide unprecedented levels of detail about Pluto's geology, atmosphere, and potential subsurface ocean. Moreover, the study of Pluto and its neighbors in the Kuiper Belt is contributing to a broader understanding of planetary systems beyond our own. By comparing our solar system to others, researchers can identify common patterns and unique features that inform our understanding of planetary formation and evolution. For example, the discovery of exoplanets with icy surfaces or distant orbits can be better understood by drawing on lessons learned from Pluto and the Kuiper Belt. In the end, Pluto's story is one of constant discovery and redefinition. From its initial classification as the ninth planet to its reclassification as a dwarf planet, Pluto has continually challenged our perceptions of the solar system and inspired new lines of scientific inquiry. As we continue to explore and learn from this enigmatic world, Pluto remains a symbol of the unending human curiosity that drives space exploration. Its mysteries remind us that the universe is vast, dynamic, and full of surprises, with each discovery bringing us one step closer to understanding our place in the cosmos.